Hello everyone, my name is Leonardo and I'm going to present the results of our research automatic evolutionary settings of machine learning methods for buildings thermal loads prediction. This is our agenda: the introduction, data and methods, experimental results, and finally the conclusion. Let's talk about the introduction. The population growth could lead to an increase in energy consumption around 30% by 2040. The energy consumption of buildings in developed countries can increase from 20 to 40%. In some cases, this consumption could surpass industrial and transportation sectors. Improving energy performance can lead to 20% reduction in greenhouse emission, and the energy performance is considered a key element in achieving sustainable development. So, energy simulation then plays an important role in building design. There are some advantages that simulation tools allow to compare several scenarios, identifying energy saving potentials and also evaluate the energy performance. But there are some disadvantages. Simulation models require calibration and an advanced knowledge of a specialist, and this can become a time-consuming design cycle. In this study, we'll focus on heating loads and cooling loads. So let's talk about the simulation models. There are three broad groups: the calibrated building models, simulation models that adjusted physical models adjusted by historical data. They require expert knowledge. The so-called gray box models that blend simplified building models with historical data, and black box models that find an input-output relationship based on measured data. And in the last few years, we have an increasing interest in black box models due to the development of sensors and IoT, and also the cheaper computational, and also these models are cheaper computational alternative. So then, machine learning models or machine learning methods, they have been extensively used as black box models. For example, neural networks, support vector machines, random forests, and Gaussian process, and other ones. They can be seen as a surrogate model for computational expensive energy simulations, but also there are some drawbacks that machine learning performance depends on the proper choice of their internal parameters, so-called hyperparameters, and find the best parametric set can be a challenging task. So in this study, we combine machine learning methods, and an evolutionary algorithm, differential evolution algorithm, to predict the thermal loads. The goal is to find the best machine learning internal parameters in order to minimize the prediction error. So we can see this problem as an optimization problem, and we use the differential evolution algorithm as an optimization tool. So now the data and methods. We have collected from the literature 768 simulated buildings. These buildings they are built based on 18 elements. They are arranged in different shapes, in 12 different shapes. Are considered 8 input variables and 2 output variables. They are simulated. The output variables are the heating loading and the cooling loading. The input variables are some architectural information, such as the relative compactness, so shown here in B, and the another ones, they are shown here in the box C. The roof area, the overall height, wall area, floor area, and also the orientation and the glazing area, and the glazing distribution. So as machine learning methods, we use in this study, we have implemented in this study 3 machine learning methods. ElasticNet regression is a linear regression approach, a linear model that combines L1 and L2 penalization scheme. The gradient boosting is a additive model that uses decision trees, and in this additive model, the current model tries to approximate the error of the ordered models, in a so-called gradient boosting approach that focus on minimize the error in this additive model. We also implemented an extreme learning machine. Extreme learning machine is a neural network, is a single layer neural network in which the inputs to hidden weights, they are set at random, and the hidden to output layer weights, they are calculated using least squares. In order to find the best parametric set for those models, we have implemented a differential evolution algorithm. This is a stochastic population-based algorithm. It was proposed in 1996, and it uses mutation crossover and selection mechanisms to guide the search towards increasingly better candidate solutions. Here you have an example, initial population, and after the evolutionary cycle, these candidate solutions, they found the best, the minimal of this function. So here the pseudocode of the differential evolution algorithm. In line 9 here, we have the mutation and crossover procedure, and in lines 11 and 12, the selection mechanisms. This algorithm is used to guide the population towards the minimum. So we have to set the hyperparameters. They are and which them are searchable. So we have used a scikit-learn based implementation for ElasticNet, extreme learning machines, and extreme gradient boosting. For the ElasticNet, we have 2 parameters. They are searchable. For the extreme learning machine, 4 parameters, including the number of neurons in the hidden layers, and 3 parameters associated with the activation function. And in gradient boosting, there are 6 parameters. They are searchable, and the loss function of the boosting procedure, we choose the squared error. It kept constant. So this is the strategy, the workflow using in this paper, used in this study. First, we got the data set. It is divided in 10 subsets one subset is using for testing, and the another 9 they are used for training. The population is initialized, and then we set the regression model. The objective function is the mean average percentage error, shown here. Then starts the evolutionary cycle in the differential evolution algorithm. The mutation, crossover, and selection. Then this cycle chooses the the candidate solutions involving the parameters of these methods. The regression model is used to calculate the objective function, and for calculate the objective function we have used a k-fold strategy, a 10-fold strategy, and if when the stop criteria is met, the best solution is used to build the machine learning. Otherwise, the evolutionary cycle starts again. Based on this framework, we have conducted some experiments. And the differential evolution configuration, population size of 50 individuals, 100 generation, the mutation rate, and crossover probability. And here we have used 4 performance metrics in order to compare the results that are shown now. Here, the comparison of 4 metrics: mean, average, mean, absolute error, the coefficient of determination, root mean square error, and the average percentage error. From these bar plots, we can see that gradient boosting outperformed the extreme learning machine and the ElasticNet models. Here we have the distribution along the distribution of the parameters along the 30 independent runs. Here we have the hyperparameters, or the internal parameters for the heat and loading, and here we have the statistics of the internal parameters for the cooling loadings. These parameters can be used in simulating another projects as a alternative, as a first attempt. Here we have the results of our model 1, 2, and 3, using ElasticNet, extreme learning machine, and the gradient boosting. So for heat loadings, we can see that the gradient boosting produced better mean, absolute error, and the coefficient of determination that is competitive with the literature. And for cooling loads, the extreme gradient boosting outperformed all models that we have compared in the literature. This results is mainly due to the high configurable feature of the gradient boosting. There are 6 parameters to set, so showing that these results show that proper choice can improve the performance of the gradient boosting. So now the conclusion. The main findings of this study is that the combination of differential evolution and the gradient boosting reaches better performance for cooling loads, considering the test metrics and the results in the literature. We have also this model. We have also produced an equivalent behavior for heating loads, and this model arises as alternative surrogate model for early predictions of building, cooling, and heating loads, assisting specialists in the design cycle. Further research involves explore other models such as fuzzy systems, and also genetic programming to build an interpretable model such as that's shown here. We would like to thank our university and the Brazilian agents that have funded our research, and thanks for watching.